Exactly. That's why we need the question. She said that our volume is really good. So that's why we're down there. The other rooms, their numbers are way up. So they're larger, they have more stuff. We have a TV, but it's like in the corner of the wall. Next to the taking a projection. You could have told that little facility.
Hello. Hi. Hello, everyone. Any questions before I begin? No questions. Okay, so we have the PAs assigned. All right, couple of things. So we have PAs assigned. I'll list the PAs and their office hours here over the weekend. Resignations will start from next week. And I have decided on the midterm dates. And 10:30 is partly because I'm not going to be here. Yes, and this is the link to the directory, which has all the PDF slides. So in case I forget not to add, you should see here. So for example, logic slides are available actually online, but I forgot to add it here. I'm not sure. Yeah, it's not. I need to find the Google Dropbox link. But anyway, all the PDF files are going to be here. All the lecture slides are going to be here. Anything else, I'll have the links. All right, so we're going to start with our first set of lectures. Sorry. For the first topic, yes. Yes. WISE, right? Women's in computer science, right? Is that it? I got an email from you, right? Yes, that's fine. That's fine. So they want to talk about an organization for a couple of minutes. I thought it was useful enough, so I let them come. Yeah.
Oh, thank you. Thank you. Sorry about that.
Yeah, basically, if you move it along.
Okay, hello everyone. Hi guys, my name is Choi Ye and I'm the Secretary of Breaks.
And hi, my name is Kayla. I'm the graphic designer.
If you want to use.
Okay. So we're doing computer science or for short. So our student org is our mission is to like provide support in human and computing, and anyone can feel free to join our club, no matter what major and what gender you are. You're still welcome to join our club, even though you're not CS major or a male.
Okay, so some events that we host are resume reviews, craft nights, interview preps, and coding workshops. We also host computer science and information technology networking events to connect you with company employers to help you land a job or an internship.
So this year, WISC is holding our annual networking mixer that will be held on Friday, September 2nd, before the career fair. And for more information, please look out for our social media.
Okay, so one event that we have coming up is our first fall TPM, which will take place Friday, September 8th at 4 p.m. in room Old CS 2120. This is right across from the VTA room. And we also have our working plan number 1, where you can just chill and do work while also enjoying some snacks and drinks. This will happen Friday, September 15th at 3 p.m. in SAC 306. And of course, you can also find us at the CES Involvement Fair on Wednesday, September 13th.
So we also have a mentoring program application we just opened up. So like if you guys are underclassmen or transfer student, it would be a great opportunity to connect with a next member that will guide you through the study CS program. And there's also alumni mentors who can help you go through the job application process and show you how it's like to be like industry professional.
Okay, so that was quite fast, but if you didn't catch all of that, don't worry. You can find us on Instagram at SBU_Wix, or you can check out our website, sbowix.com, which has all of this information. And I also printed out some flyers for you guys so you guys can pass around. It has our Discord, our mailing list, and of course our Instagram. So yeah, I hope to see you guys soon. Thank you guys so much for listening, and thank you, Professor, for letting us.
Sure.
Okay, you guys can pass around. Thank you. Thank you, John.
All right, sorry guys. All right. So let's get back to our lecture here. Okay, so this first set of lectures may seem easy to some of you, but maybe not. But trust me, in the homeworks and an exam, you will have sufficiently tough questions to challenge. All right, so this is the basic outline of this chapter or this topic. So logic. So what we want to do is we want to develop some formalism to represent statements that either evaluate true or false. That's the key point of these statements, which are called propositions, that they either evaluate true or false. Like for example, today is Sunday. It's either true or false. Okay. And of course, there are examples of statements which may not be propositions. For example, x plus y is equal to 5. It's non-determinate. You cannot actually determine if it's true or false. And other statements. So we are focusing on statements that evaluate true or false, and then we are going to essentially learn operators to manipulate these statements, to operate on these statements, and infer some facts from a given set of these statements. Okay, that's basically the overall goal of this chapter. That is, we want to basically look at these statements and develop some mechanism to operate on them, to manipulate them, just like we have addition and subtraction to manipulate numbers. We want to have some operators to manipulate these propositions, and to be able to infer some facts, or whether a proposition is true or false based upon what is given to us. Okay, that's basically the goal of this chapter. So fundamentally, we want to we have two concepts. One is logic variables and operators. Variables are essentially logic variables are essentially variables that are either true or false. So essentially, just like integer variables, we have logic variables. They are also called Boolean variables in the CS languages. And generally, we'll use PQRT, but there's no rule as such that. But as a convention, we can use PQRT as etc. for logic variables. Operators. There are 4 operators, and we'll see what they mean, or what does it really mean by these 4 operators. What do we mean by these 4 operators? So not, and, or, implies. These are 4 basic operators. There are many more operators, but these are the most basic. Everything else is kind of composition of these operators. Okay, so we're going to focus on these 4. And then we'll see how other operators can be derived from these. So these operators can be used to operate on these variables or the statements, and what you get are essentially what is called upon statements. These are essentially statements. They are essentially, in some way, they are expressions of propositions and operators. So here these operators, these 3 are binary operators, and or implies, that is, they take 2 operands. Okay, P and Q. Not is a unary operator; it takes only 1 operand. And that is why these are just 2 examples of compound statements. Okay, so let's look at what is the meaning of these operators, or how does the operator change the proposition. Okay, and the way we represent that, the way we represent the meaning of an operator, or in general, as you will see, meaning of compound statements is what is called a truth table. Truth table essentially has 2 parts. One is the statement that we are trying to evaluate, okay, which is actually on the right hand side. Not of P is what we are trying to evaluate in this case, and right hand side is essentially all possible combination of input values. So here the only input is P. So essentially what this table is telling you is what is the value of not P given a value of P, right? So this says basically if P is true, not P is going to be false. If P is false, then not P is going to be true. So truth table essentially is in some way a function, right? It's telling you input and output. And since we are representing this function as a table, this table better have all possible combination, all possible input values. So here there are only 2 rows because there is only 1 input variable and only 2 possible input values. Okay, so the truth table is a complete representation of what an operator can possibly be. So not essentially inverts the original value of the logic variable of the statement. Okay, P and Q. Now this is table for P and Q. As you can see on the right hand side of this, or sorry, on the left hand side of this table, we have 4 combination of input values because there are 2 input variables, P and Q. So depending on the combination of the values of P and Q, the expression P and Q will have different values. So what happens to the not statement is that it is true only if P and Q both are true. Otherwise, it is false. So there are 4 possible combinations for true and true. P and Q is true. For other 3 rows, P and Q is false. Okay, this is extremely basic. I still want to make sure that you guys understand it. So do we understand what a truth table is? What is the purpose behind a truth table and what purpose it is serving? Truth table essentially is a representation of what a function is. Well, we haven't really formally defined what a function is, but informally, basically, it tells you that what the expression evaluates to. Okay, essentially, the truth table is telling you what the given expression evaluates to. And the only way to represent this information in a truth table completely is to have all possible combination of values for the input. So there are essentially 2 parts of the truth table. One is the right hand side where essentially is the expression that we want to evaluate, and the left-hand side is the combination of values of the input variables. All right, so similarly, P or Q. Here, P or Q is in some way a reverse concept of AND, not really reverse in the traditional sense of AND, but it basically is false if both the values are false. Otherwise, it is true. So if you look at P and Q was true if and only if both were true. Here, P or Q is false if and only if both are false. Otherwise, it is true. So it kind of makes sense because OR in the connotation of OR as we use it in our language is either or, right? So P or Q is true if either P or Q is true, and P and Q is true if P is true and Q is true. So in some way it matches with our intuition. Now this one is slightly complicated. By complicated I mean it's slightly non-intuitive. And I have a next slide to get into more behind the intuition behind this or why it makes sense. But let's see. So P implies Q is another expression which has a slightly strange table. But essentially, the way to remember it is false only if P is true and Q is false. So only if it represents a counter example for the implication. So implication is saying that P implies Q, that is, if P is true, then Q is going to be true, right? That's what it is saying, right? So it is going to be false if that is somehow negated. When will that be negated? If P is actually true, but Q is false. So that is essentially where P implies Q is false. Otherwise, it is true everywhere else. Okay? So the key to remember is that P implies Q is false is true by default, but it is false if it essentially is it negates the statement that it is representing, that is intuitively representing. That is, it will be false if P is P is true and Q actually is false when it should be true. Okay. Now. So the other way to look at it is that we may have some intuitive notion of implication, of what implication means, and this may conflict with what you may have something in your mind intuitively. But the point I'm trying to make by the statement here is that it's not that we are coming up with a truth table based upon some intuitive meaning of implies. It's the other way around. So for this truth table, we basically call it an implication truth table. Okay, and the next slide actually gives a little bit more, digs a little bit more into why you may find it counterintuitive and why it still makes sense as a truth table. Okay, so let's look at an example. So that's just an example. Okay, the point of the slide is only because when I was studying implication, when I was a student, it kind of the truth table kind of confused me. I kind of did not like the fact that. This thing, why is it true here? Why the last two rows are true? Essentially, it wasn't intuitive to me. And the simple answer to that is that, well, there is a truth table and someone gave it a name, implication. That's one way to look at it. But it actually does make sense intuitively in a formal sense of what implication should mean. And this example is just trying to represent that intuition. Okay, so let's say P is sky is blue and Q is its daytime. Okay, this is an example where I'm trying to dig into what P implies Q should actually be. Should it be true or false? Okay. Now I'm looking at two situations, two settings. In night time, P is false and Q is false. Okay. And there is another setting, of course, I have where it is a cloudy day where P is false but Q is true. Now the question that arises is that intuitively should P implies Q hold at nights or cloudy days? So that's where basically you can test your intuition. Where does it make sense for P implies Q to hold And the way to think about it is this claim, P implies Q, is still a valid claim. These two instances of night and cloudy day do not actually invalidate this claim. So P implies Q can be looked upon as a claim that is being made, and the claim is going to be false only if there is a counterexample to it. And the only valid counterexample is if P is true and Q is false, right? So in some way, this example is basically giving you some intuition behind why P implies Q. It makes sense for it to be true, even if P is false, and Q can be anything. Or why does it make sense for P implies Q to be true when P is false, irrespective of what Q is? Okay. But if it is still counterintuitive to you, I wouldn't worry about it. You should in some way just accept it, this truth table, as the truth table for implication. Okay, even if it is a little counterintuitive. Okay, but it is actually it does make sense. Okay, if you look at P implies Q as a claim being made. Okay, so with this basic foundation of logic operators and variables, we are now going to look at expressions or logic formulas, and we are going to see how to evaluate them or what does it mean. For example, this is a formula, right? This is composed of ands and ors. There's no or here. There are ands and nots. And there are parentheses there. Parentheses, of course, just to avoid ambiguity, just like in arithmetic expressions. So or and nots are not very different conceptually than mathematical operators like addition, subtraction, multiplication, division, except that they are operating on numbers, and these operators are operating on logical statements or variables. Or they may also be operating on the actual values, true or false. So here we are using variables, but I could have had P replaced by a true T also, right? Just like numbers, just like addition and subtraction, we can operate on variables as well as actual numbers. So here also, an expression can be composed of variables or actual constants. But in the logical world, there are only two constants, true and false. Okay. Now the question is, how do I make sense of this expression, or how do I actually write down what this expression evaluates to? So the simplest way is to construct the truth table. Right? Truth table will essentially have again two sides. One is the all possible combination of input values, and the right side will be the actual value of the expression for that combination. Note that there are only four possible combinations of input. No matter how complicated the expression is, the number of values is 2 raised to the number of variables. So if the number of variables are 5, then you'll have actually 32 rows in this truth table, because you have to look at all possible combination of values. I presume everyone understands where I get 32 from. Each variable has 2 values, so the number of combinations are 2 raised to the number of variables. So in this case, there are only 2 variables, so there are only 4 rows, and we're looking at all possible combinations, and now we need to evaluate for each combination what the value expression is. We can do that one at a time manually, and that is essentially the only way to build a truth table in some sense. Well, at least one of the ways to do it. So in this case, let's say true 2. What should this be?
False.
False. Well, this is false, so this is going to be false, so this is true. This is going to be true, right? And this is true, this is false, so the whole thing is going to be false. Basically, this thing is going to be false. I wonder if I have a slide which goes through the details. It does. Okay, so there is one example. Let's look at this example where P is true and Q is false. So what is happening is we basically plug in true and false here, just like we evaluate a mathematical expression, and see what happens. So this is going to be not a false, so this is going to be true. All right, this is what we get the truth table as. You can confirm it. Well, if you look at these two values must be same because this expression is symmetric in terms of P and Q, right? P and Q have a equal representation in the expression. So the values of P and Q interchange shouldn't change the value. So that's why these two are true. Now these two you need to evaluate for all false and when both are true or when both are false. Okay. All right. So I skipped one slide. Yeah, this was basically what I said. That there are 2:n combinations of input values that we need to look at. Okay. Any questions? So what we have done is we basically have looked at. We have introduced a concept of propositions, which are statements that are either true or false. Now, to be able to develop more complicated statements, what is called compound statements, we have looked at certain operators. We have looked at 4 operators: or, and, not, and implication. And using these 4 operators, we can actually create compound statements. The compound statements are essentially statements just like mathematical expressions, which are formed of operations and variables or constants. Okay. Now, if you have an expression in just like arithmetic expressions, you evaluate it starting from the lowest parenthesis and so on and so forth. Same way you evaluate a logical expression. The only difference is that there in 2 plus 2 we actually add. Here to find out what is true and false, you have to look at the truth table or know what the AND operator means. Essentially, we are looking at the truth table of the operators to evaluate these sub-expressions within the parenthesis and so on. So that is how we get this truth table for this formula. Okay. All right. So now let's. I don't think I'm going fast, but by the pace I'm going, I may be done with this chapter today. But that's okay. We'll spend a lot of time doing examples from the book, either in the remaining time today or the next class, and of course you'll have recitations. So I think this chapter is probably the easiest chapter, and the next chapter, which is related to this quantified statements, that's where things started getting a little complicated. All right. So, but feel free to slow me down if I'm going too fast. How do you slow me down? Well, you can ask me to slow down, or you can ask me questions. Okay. If you don't understand, or actually in the past, and by the way, I'm very happy to do that. In fact, of course, you won't feel the need now, but in future, in the remaining classes, people have asked me to repeat a whole concept all over again. So I've gone over it, the concept that I taught all over again from scratch. So I'm happy to do that. Okay. All right. So here equivalence. So now we want to look at whether 2 given expressions are equivalent. What do we mean by equivalent? Well, there is only one definition of equivalence, that they have the same truth tables, that they're exactly the same. They evaluate to the same constant. There are only 2 constants, true or false. So they evaluate to the same constant, irrespective for all combination of values of the input variables. That's what equivalence means. How do you test 2 formulae are equivalent? Well, you can create a truth table for each one of them and compare the truth table. The truth table should be exactly the same. That it should have the same rows, right? That is how you evaluate equivalence. But that is a little tedious, right? Because sometimes maybe we can do something more intelligent. Just like, expressions. Well, in case of mathematical expressions, if somebody gives you 2 polynomial expressions and you want to actually determine if they are equivalent or not, you are not really going to draw or look at the truth table. Well, in the case of arithmetic expressions, the truth table is infinite, right? Because the number of possible combination of values of integer variables is infinite. And even if you were to draw a graph, that is not how we actually determine equivalence of 2 expressions, right? What we do is we essentially somehow manipulate them, maybe factorize them, maybe take things on both sides, cancel out things, and see if the left hand side is the same as the right hand side. So we do some manipulation, right? Rather than actually create rather than actually draw a graph for each one of them. And so here also there is something like that. We don't do things like cancellations, but we kind of manipulate both expressions so that they kind of evaluate to the same simplified expression. Okay, or essentially we try to manipulate one expression so that it becomes the second one. Okay, so to do that we need some tools. We need some basic axioms. Okay, in order to manipulate expressions. Okay, and these are essentially axioms which can be verified by drawing the truth table, right? So firstly, this and or operators are commutative. That is, P and Q is the same as Q and P. And this can be easily verified by looking at the truth table. You can look at the truth table of an AND operator. It's symmetric with respect to the two operators. So this is obvious. This may not be very obvious that if you have and, if you have two ANDs, or if you have three variables, you're taking an AND off, you can actually do it in any order. You're going to get the same result. So these two operators are also associative. So this is what associativeness means in the context of expressions, and this is what commutative means in terms of in the context of expressions. Like for example, addition, subtraction, and multiplication, they are both commutative, associative, and they are both commutative and associative. Distributive generally is with respect to multiple operators. Okay, so here we also have this axiom that if we have two operators, that is P and inside we have an OR, then the equivalence law says, or the axiom says, that this is actually equivalent to taking an AND of P and Q and then ORing it with P and R. So P actually gets ANDed with Q as well as R, and then you take an OR of those two sub-expressions. And similarly for OR and AND. Now this is not very obvious. It's not obvious at all, in fact. How do you know this, right? But you can verify it using our truth table. Maybe the next slide has the truth table for these. No, it doesn't. So this is easy to verify, and let's do that. Let me spend some time, trying to do this this one. So we'll do the 3A. The first day we are going to prove the first axiom. And how are we going to prove it? We are going to basically create a truth table. I think Google Doc may be much cleaner. And so I'll actually share it right now. So I need to make it commenter so that you can see my comments, but I request you not to add comments yourself. Because if I make it just viewer, then you cannot see the comments that I add. Sometimes I add comments actually to make it stuff. To keep it clean, I sometimes add comments. Okay, so I'm going to add the slides link. I will do it later on. I generally call this class notes. Okay, all right. So we are trying to prove you guys are fast. So again, and an OR. Let me see if I can copy it once. This is fine. You guys are blocking my view. That's right. All right, these are distributed, right? So what we want to show is we want to show that P or. I don't know what is registered now. Okay, maybe there's a line. This is what we want to show, right? So let's create the truth tables for this. Truth tables. Truth table. We're going to create one truth table. So it will have 8 rows because there are 3 variables. We're going to have 8 rows, right? So true to true. So this means basically P. Okay. So the way the truth table is going to look like, I'm going to PQR is what I'm going to write first, and then I'm going to write what this evaluates to, and what the next one evaluates to. Right? That is what the truth table is going to look like, and of course, I'm just not going to have comma. I wonder if there's a way to stop this. There must be a way. Of course, I can stop sharing. Okay, that's fine. I'll manage one. Okay, so what is this expression when all of them are true? Well, it's going to be true, right? Because even or and no matter how you do them, how you manipulate them, if everything is true, it's going to be true. Right? And same thing here. If everything is true, it's going to be true. That's too obvious, right? Now let's look at true to false. So only R is false, everything else is Q. So R is false, so this is going to be false, but it doesn't matter. P is true. So this is going to be true. And since P is true, this is going to be true. And sorry, this should be P. Somebody was pointing out, I guess. And this is going to be true. So we have true. And now, of course, the only reason I'm doing this is so that you kind of do. So I want to do one complicated example of how to do the truth tables and how to come up with this 8 combinations, I guess. With P being true, there are 4 combinations of Q and R. Now here, if Q is false, then this is going to be false, but it doesn't matter. So this is going to be true, right? And if Q is false, this is going to be true, and this is going to be true. So it's true. So as you can see, the truth tables are matching up. Now, if P is the only one that is true, this expression is true, and this expression is true, and this is true. Right? Because P is in some way the determining factor. But that doesn't mean if P is false, then we will be false, as we will see. Now, so here we looked at 4 combinations with P being true. Right? We looked at all 4 combinations of Q and R. Now we are looking at 4 combinations with P being false. If P is false, this doesn't help. But luckily these 2 are true. So this expression is true. We're getting too many truths actually. This expression is very maybe it's a tautology, we'll see. So this one here, Q is true, so this is true. R is true, so this is true, so this is true. So till now, our claim seems to be playing out valid. So now only Q is true, So this is false and this is false. So we actually get a false. Only Q is true. So this is true, but this is actually false. So we get a false because we are taking a true and false. This actually expression is symmetric with respect to Q and R. So this is going to be the same as the previous row. I don't need to really check. And if everything is false, then of course it's false because we are not taking a NOT, we just OR and AND. So if you look at the OR and AND tables, when you have the input variables as false, you only get false, whether it's AND or OR. So this is kind of easy for me to do that, but you can check it. So these two rows, in some way, I did it using a shortcut in my mind. But you may have to do it manually, but that's fine. But the point is, here you see the truth tables are exactly the same. That is why this equality holds. Okay, and this is just a point. This is just one example of how to check equivalence of two expressions. Now that we know these axioms, and of course this can also be verified. I think, no, I shouldn't say that. I actually don't know. I was just about to guess that the truth table gets inverted, but I wouldn't say that. Yeah, I'm not sure. So you have to manually evaluate. Now we're going to we can use these rules to actually prove equivalence of more complicated expressions. Just like in algebraic expressions, right? Or polynomials, we have some basic rules that a cube minus b cube is a minus b into a square plus I think ab plus b square. So we have these laws, and then we use them to prove more complicated statements. And similarly, we're going to do that here also. So here there is this De Morgan's law, which we will try to prove because it is actually hold on one minute. Yes, so this slide does not do the De Morgan's law. Okay, fine. So let's do the De Morgan's law now. De Morgan's law are actually very powerful laws, which essentially they have a kind of a pattern. What they're saying is, if I take an and outside, if I take a NOT outside an and if I want to push the NOT inside, then you can do so, but the operator will get reversed. So the AND will become OR, and OR will become AND. So that is what the De Morgan's law is. Of course, I've just written it, and you will prove it. The only way to prove it actually is truth table. There is no other way because these previous laws are not going to help you there, right? Because these previous laws don't really help you prove this. So let's prove this also. So I'm going to prove one of them. Second one is basically similar. Let me cut and paste. I doubt it will work, but we never know. It did. Nice. Okay, so we want to prove this, right? So we're going to do the truth tables. And here we only need 4 rows. So the truth table is going to be basically combination of PQ values, and then what this evaluates to. These are the columns I'm writing basically. And what this evaluates. Okay, so we're going to look at true. So if both are true, this is true, but the NOT will make it false, so this is false. And here, this becomes false, this becomes false, and false or false is false. Now you have true, false. True, false, so this is false. So this becomes true, and here this is going to be true, right? NOT of Q is going to be true, so this whole expression is going to be true. Similarly, because it's symmetric, this third row is going to look like the same. And now the fourth row is I don't know, but let's see. If both are false, then the inside is false. Of the first expression, this is false, so the whole thing is going to be true. And here, Both are false, so this is going to be true and this is going to be true. So it's going to be. So we just use a truth table to prove the equivalence or the correctness of the De Morgan's law. Any questions? So I'm just doing something extremely basic. Truth table is like it's an undeniable proof. It's basically too low level of proof. There's no questions about it, right? Because it's basically what it is doing is it is basically testing the equivalence with a very by the definition itself, that it actually evaluates to the same value no matter what the input variable values are. Okay. So similarly, we can do the other De Morgan's law. I'm just skipping that. We can try it, but you're going to essentially get the same methodology and we get something very similar. Okay, questions? Everything is clear to everyone? Very basic. Okay, so this is a slightly more complicated example where we are trying to prove equivalence using some manipulation as opposed to a truth table. Right? Now, so this slide is essentially saying that you can show the equivalence using truth tables, which we actually have done in a few examples till now. Now we're going to apply the second technique, which is using some laws. So we look at this. This is not very obvious, right? This is not obvious at all. Of course, you can do it using truth table. That will work. But let's try to do it. This slide is trying to do it using some equivalence, applying some laws. I would have liked that if this didn't exist and we were to actually do it in class, and that is how I normally do it. But unfortunately, I don't know, for whatever reason, I have a solution on the slide. But otherwise, it would have been fun to actually do it from scratch. As you can see, just because the solution is written, it loses a little bit of fun. But anyway, if you look at this, it kind of seems obvious that I should apply the distributive law. Why the distributive law will help actually is because there's a not Q here and there's a Q outside. So some simplification is bound to happen because you have not Q applied by this. And that simplification is what may get you the simplified expression. That's basically the idea. So if you look at this, it kind of seems obvious that you apply the distributive law because things will get simplified because of not Q and Q appearing here. So this is just because of commutative, I'm just doing it the other way around because the way the distributive law is written is it's one operator then the expression, a binary expression. So this is application of the distributive law, that is Q and P or Q and not Q. This is false. Okay. So you have Q and P or false. Now by the truth table, this false doesn't play a role. The value of this is the same as this. In fact, that should be that should be an axiom. An axiom should be, which I don't write it, but it's kind of obvious that P or any P or false is equivalent to P. This could be any expression. By the way, P variable can be replaced by an expression also because okay, the other is P and sorry. Yes, so this is fine. Right? Do we agree with this? If not, you can check the truth table. You can basically draw the truth table for each of these and you get it. But essentially what this means is, if this is false, okay, then the value will determine on what this is. And if this is true, then it doesn't matter what P is. It will always be true. So same thing, you can have it in AND operators. We have a variable and true. This is going to be equivalent to P. And sometimes, by the way, we use the sign equal. The only difference between equal and equivalence is that equal is a little too strong. Equivalence kind of means that they evaluate to the same value. Equal means the expressions are exactly equal, but it's a minor difference. So you may see me writing equal to as we do it in expressions also. Okay. And here P and false is going to be false. Irrespective of what P is. Okay, so in some sense, I've used one of these axioms here. to go from the third statement to the fourth statement, right? Or false is this P and Q, and P and Q is the same, Q and P is the same as P and Q, and that is what, essentially we have proved the equivalence of these two expressions. And of course, we could have done it using truth table also, but truth table is a little tedious. And it can get very, very tedious if you have n variables, then 2 raised to n is huge. You don't want to be creating a truth table with 22 rows, etc. And of course, here, of course, it would have been simple, only 4 rows, but okay. All right, so this is what we did. Okay, now these are certainly very non-intuitive. Okay, and my only answer to why these are true is you can look at the truth tables. Truly, that is truly the only solid answer to this equivalence. They are intuitively also true. Intuitively, they are equivalent, but it may not be intuitive to you guys because it takes a little while. Because implication kind of does play with our intuition quite interestingly. So P implies Q is actually equivalent to not P implies not P. Sorry, not Q implies not P. You can argue about it, and basically it means that if P is implying Q, and if Q is false, then P cannot be true, right? Right, because P implies Q. So if Q is false, P cannot be true. So P must be false. So that is the illusion. Not Q implies not P. Okay. And this basically says not P or Q because either P is false or Q is true. Because P can only take 2 values, right? True or false. If P is true, then Q is going to be true. If P is false, then it's false. So that is why this comes in. Not P, either P is, this basically says either P is false or Q is true, which is what implication is all about, right? And of course, these two are equivalent by De Morgan's law. Second and third are equivalent by De Morgan's law. Okay, so these you kind of should know actually. These are very often used. So you can verify them using truth tables, and of course, verbally I did verify them using truth tables, right? Because P implies Q is false only if P is true and Q is false, and you can actually verify them. But you should remember these expressions. Okay, so this expressions, at least the first two. The third, of course, follows from the De Morgan's law, and generally the third one we don't use it very often. But first and second is very, very common. You will be using it very often, so you should really remember the first and the second. Okay, that P implies Q is equivalent to not Q implies not P, and not P or Q. So these two you really should remember it, and the only way to remember it to actually really understand it, to be convinced that they are intuitively meaning the same thing. That is the only way to really, really remember it. Otherwise, you'll be cramming it and then you'll forget it. Okay. So it's easy to confirm using the truth tables. We can look at an example and see, right? Now this is an interesting example. Alex is a father, and Alex is a male. P is this statement. Q is, so P implies Q in this particular case holds. So this by the way, this is just an example. This being true for these expression doesn't prove the equivalence. Okay, this is just a check rather than a proof. Okay, what I'm doing here is just checking the equivalence of this. By checking, I mean just sanity check. It's not really a proof. What I'm doing here is not a proof. So in this case, P implies Q holds. Does this hold? Not Q implies not P. That is, if Alex is not a male, then does it imply that Alex is not a father? Yes, right? If Alex is not a male, then it does imply that Alex is not a father, right? So this kind of holds. If P implies Q holds, then this holds. Now let's look at this. Not of P or Q. Not of P is Alex is not a father, or Alex is a male. Does that statement make sense? Alex is not a father, or Alex is a male. Right? Because either Alex is a father or he's not a father. If he's a father, then he's going to be male. So that statement does make sense, that Alex is not a father or Alex is a male is a valid statement, kind of makes sense, right? Okay, and you can look at this. This will be a little complicated, but I think the way to argue about the third is you don't have to remember the third one because third follows from the second one using the De Morgan's law. Now, De Morgan's law you should remember. So, okay, so of course you should know these. This is very simple. You should know these. You should know the De Morgan's law. They are used very, very often. Okay, so you should know these. And you should know the first and the second equivalence of the implication of it. Okay, any questions? No questions. All right. So there are these concepts. Okay. In some way, these are terms that you should know the meanings of because you may have exercise saying that prove something is tautology. Tautology means a formula that is always true. That is, if you look at the truth table of that expression, the right column is going to be all true. That is what a tautology is. Tautology is something that is always true. Now these are examples of tautology, right? If you try to do the truth table of this, of course you're going to get a true, right? P or not P. Of course there's a tautology. Now this one is also a tautology because why is this a tautology? Can someone tell me without actually telling me to create a truth table? Can you look at it and tell me why is that a tautology? The second one. Yes.
Because like one of the parentheses has to evaluate true because one value is true, another value is false.
Why does the first statement hold? Why one evaluates to false and the other one?
Because one is just a not version of the question. So like,
Yes, by the De Morgan's law. Yes. So that's what I wanted to hear. So basically, the second part is just the not of the first part. The second parenthesis is the not of the first part. So this is actually in some way P replaced by P and Q. That's basically what it is. Because by De Morgan's law, this is actually the not of this. And that is why one of these sub-expressions, one of these parentheses has to be true. Because one is the not of the other. Do we understand? Questions? Of course, you can always do the truth table, but you know, at this point, or at least not at this point, by the point of one more lecture when we have done a lot of exercises, you should not rely on truth tables. You should be able to see these things in expressions and be able to evaluate expressions, etc. Right? So conversely, contradiction is a formula or an expression that is always false. Right? Like for example, P and not P, that is always false. P and not P is now going to be true, right? So you can come up with that. Biconditional is an operator, and it's a double arrow, and it's basically equivalent to P implies Q and Q implies P. Okay, this is not a tautology. This is not always true. Of course, right? We know that, right? I mean, just two statements doesn't mean they both have to imply either, right? And in fact, this is a very strong condition between the two. In fact, it is we use it actually colloquially that P is a necessary and sufficient condition for Q, something like that. Okay, and this is equivalence back. So this is basically, and you can check that this is true if and only if both are the same values. You can check using a truth table that this is true only if both are the same values. Okay. Yes. Sorry.
So in the tautology example,
Second, sorry.
in the top example with P and Q or not
Yeah.
P or not Q,
Yes.
is it correct to say that the left is the inverse of the right?
That's what I said.
So that's the correct.
That's exactly what I said, right? So yeah. Inverse is not the right word, not.
Yeah. Okay.
Yeah. So basically, so if you take a knot of this, what do you get? By De Morgan's law, you're going to get knot of P or knot of Q, right? And that expression is basically taking these two and ORing them, right? That's what it is. and that's why it's put on. Okay? Any other questions? No. Okay, so this slide is talking about exactly what I was saying, necessary and sufficient conditions, and you may have come across this term. If not, then you will when you do proofs or when you do some theoretical stuff for mathematical proofs. So, formally, when we say P is sufficient for Q, what we are meaning to say is that P implies Q. And it kind of makes sense, right? By the meaning of the word sufficient. What sufficient means is that, you know what? P by itself can guarantee Q. Now, Q may be true for other reasons also, but P is sufficient. But, okay? So P is sufficient for Q essentially means P implies Q. Okay? And P is necessary for Q means this. Do you see why this intuitively means this? P is necessary for Q means that P has to be true for Q to be true. Right? That's what it means, right? That means that if P is false, then Q cannot be true. Right? If P is false, then Q must be false. That's what it means, right? That's why you get this not P implies not P. P is necessary for Q means that P has to be true for Q to be true. Another way of saying that is P is false and Q has to be false. And that's what it is. Not P implies not Q. Okay? And as we saw in the previous slide of the day, this is the same as this. And you can argue also intuitively. P is necessary for Q means if Q is true, then P has to be true. Right? Because P must have been true for Q to be true. So Q implies P. And so sufficient means P implies Q, and necessary means the other way around, Q implies P. And when both of them are biconditional, there is this biconditional between them, P double arrows Q. It essentially means that this and this is true, right? By the previous slide, and essentially means that P is necessary and sufficient for Q. Yes.
So if P is sufficient for Q, would that be a relation because R could also be sufficient for Q?
I don't know what relation means. And we haven't talked about relation, and relation is a completely different concept. I don't know why you're bringing up relation. So P is sufficient for rule. We are talking about logical statements. They evaluate true or false. Okay. Now P is sufficient for Q has a logical meaning. And P and Q are logical variables. So P can be true or false, Q can be true or false. P is sufficient for Q is a logical statement which is either true or false. Okay, what it means is, well, actually the equivalence of that is P implies Q. And in English, what do we mean by P is sufficient for Q? We kind of mean that, you know what, if P is true, then Q is going to be true. That's precisely what it means in English. And that is also mathematically, we are trying to, we are saying P implies Q. Okay? So there's no connection to the relation. Okay, and yeah. And we haven't talked about relation at all, and we may not in this class. Yes. Any other question? Okay. So we understand this very well. Implication is a little tricky. It is a little tricky, and the best way to get around it is don't let your counterintuition overrule you. Okay. It may be slightly counterintuitive, the truth table, but you really have to accept it, and then you can try to convince yourself, but don't argue against it. Let's put it this way. Okay, it took me a while also to be very convinced. So it's not very simple. So that is one thing. So first thing, you should be you should accept this truth table, and try to convince yourself through some examples as we have in the previous next slide. But it still may be counterintuitive to you. Don't let that happen. So that's one thing. Accept the truth table. Second is these equivalents. These are going to come in very handy, extremely handy. The first and the second. You should really know these, and we will use them very often, or you will use them very often. If you have these, then you are essentially the second, at least the second statement demystifies implication, right? Whenever you see implication, if it's confusing you, just replace it by the second thing, and then you are done. So you can, in fact, obliterate implication from your challenges by just replacing it wherever you see it by the second statement. You can always do that, right? Any exercise involving implications, if you find it challenging or if you find it, it's confusing, just replace it by that. Story ends. Okay, then you don't have to deal with implication at all. So that's another way. But irrespective, you should really know these two expressions for implication. And that will really, really help. So I also have this slide. Let me just look at the overall picture. Okay, so we will not do the inferences. Yeah, I don't want to do inferences. So let me skip this slide. This is just kind of a repetition with about necessary and sufficient. Let me just go this slide. So if you look at this, actually, this is kind of very interesting. Actually, I was when I was looking at the slide. So this is kind of extremely counterintuitive, or it kind of doesn't make sense in some way, but mathematically, we need to make sense of it, right? So let's say prosecutor who's trying to prove the defendant is guilty, right? He makes a claim that if defendant is guilty, then he had an accomplice. That's his claim. He's making an implication claim, right? He implies claim, right? If defendant is guilty, then he had an accomplice. Now, defense attorney, let's say that's not true. You may think that defense attorney is saying something meaningful, but actually, if you mathematically evaluate his statement, his or her statement, it actually implicates the defendant completely, because what it says essentially is something which is which may not make sense. So he's claiming that the statement is untrue, right? Right. So essentially, what the defense attorney is saying that this implication is untrue. That means he's claiming that P implies Q, not of P implies Q is true. So that is what the defense attorney is claiming. Now let's evaluate this. Not of P implies Q is not P or Q, right? Because we have replaced the implication by this expression. Then we apply De Morgan's law. Well, this is a weird way of applying it, but it is applying the De Morgan's law essentially because it is taking the knot outside. We take the knot outside, and it's P and of knot of Q. It's kind of a weird way of applying a De Morgan's law, but it's fine. Knot and knot cancel, so you get P and not Q. So the defense attorney essentially is claiming that the defendant is guilty and the defendant had an accomplice, which is extremely counterintuitive to what you would make sense from the previous two statements. The point of this is that implication is a mathematical. It's a mathematical concept that has no ambiguity, and that is how it should be looked upon. Okay, and in legal terms, by the way, this is not some tricky slide that I have here. Legally, actually, that is what it will be. It will be taken to mean actually dependence, because in professional legal settings, they are very, very formal, and the logical statements are looked upon as the way we look at them as mathematical. Okay, so when they use the term or, and, nots or implications, etc., they have mathematical meanings in the legal documents. Okay, and those are very, very careful. So it is kind of important to understand what implication mathematically means. Okay, so this is an example to tell you how counterintuitive implication can be sometimes, or at least the inverse of implication can be sometimes. Okay, I am going to actually stop here because I don't want to go through this. This is slightly more complicated. Yeah, I don't want to leave it halfway. And yes, any questions? I'm going to be here for 5 minutes. If you have any questions, I'm happy to answer those. Yes.
No. Not yet.
So I kept looking up and moving my
And he also said, your diners if you didn't read this too, right? I don't think you made wrong.